Okay, so in today's class, which is going to be a short one, we are going to draw a picture of SL2R and SU11, which we have seen are conjugate subgroups of SL2Z. Okay, so the first thing to draw the picture is this theorem, which states that SU11, hence also SL2R, is diffeomorphic to the solid torus, right? To the product, to the, let's say, topological product of the circle with the disk. Okay, and the proof. Once one has the formulas, it's not easy. I'm not going to say how one obtains the formulas. Just define first from SU11 to the solid torus by, if they give you a matrix in SU11 where it's the entries are complex numbers alpha, beta, beta conjugate, and alpha conjugate, and such that the determinant of the matrix is 1. If you are given such thing, then you send it to this pair. So alpha divided by its norm. So remember that since the square of the norm of alpha minus the square of the norm of beta is equal to 1, alpha cannot be 0. We saw that last time. So this is always allowed, and this quotient is always allowed, right? So so here is the basic computation that also tells you that this beta divided by alpha is indeed in the disk, right? In the open disk. Okay, so we have a function which can be easily seen, if you represent alpha and beta like as in the form x plus iy, you can see that the correspondence rule is of class C infinity inside this group. So phi is infinitely differentiable. Okay, and now let's define a map. So let's define the inverse of phi. So given a pair of elements consisting of a complex number of norm 1 and an element of the open unit disk, well, just take that pair to this matrix, which first of all notice that this one is the complex conjugate of this one. This one is the complex conjugate of this one, and when you take the determinant, well, you obtain this. This is quite easy, right? Because here this one is common denominator. So this times this in the denominator, the square root disappears. Minus, and also here it disappears. And then on top we have this one. We pull out the square of the norm of W as common factor. So this one cancels, and then we are left only with the square of the norm of W, but W was in the circle. So it's 1, right? So this matrix is indeed in SU11. And then again, if we represent W and Z in the form x plus iy with x and y real, and then we develop this formula, this in terms of the of x and y, one can see that C is also of class C infinity. And also a direct computation shows that phi and psi are mutually inverse. So they are mutually inverse diffeomorphisms. Okay, so indeed SU11 is diffeomorphic to the solid torus. So SL2R is as well. And now let us see, knowing that it's a torus, let us see in the torus, which of course this one we can draw it, right? I mean, we can draw the circle and then times the disk, right? And then actually kind of draw and have a concrete picture of the torus, right? So, and in the end, right? In the end, obtain what we know. So and then we can maybe obtain a picture inside the picture of the torus for the regions occupied by, let's say, the elliptic elements, by the parabolic elements, and by the hyperbolic elements. Right. So to do that, so take an element in the solid torus, and for the associated matrix, compute its Möbius trace. So when you compute it, so recall, so this one has determinant 1. So we only need to take this plus this square. So that's here, because the determinant is 1. So that's all we need. And this, of course, gives me, since here it's W and W conjugate, we obtain this is 2 times the real part of W, and then square becomes this. So it the Möbius trace of that matrix, of the matrix that corresponds to this point, is either elliptic, parabolic, or hyperbolic, if and only if, well, this you have to compare it with 4, right? So you compare it with 4, and then these 4 and the other 4, you can cancel them, and then you obtain this, right? If and only if this happens, if and only if this happens, right? And then you see, for instance, in the parabolic case, this seems like the equation of a circle, right? And then this one looks like an inequality defining an open disk, and this one looks like an inequality defining the complement of an open disk, right? Of a closed disk. I'm sorry. All right. So let's see. Let me draw, let's say, here the the x-axis, where I draw, let's say, the real part of W, and some other axis where I draw the norm of Z. Right? So in this re of W and norm of Z plane, this equality does define a circle, right? The unit circle. Okay, and now it defines the unit circle, right? But then now here I have the norm of Z plane, right? But so if instead of that I draw, I draw the whole Z plane, not the norm of Z axis, but the Z plane, you see, orthogonal to to the real of W axis. So this lives in a plane orthogonal to this real of W axis. So here you have here is orthogonal, and then here I'm drawing a translation. So here you also have orthogonality. Oops, orthogonality here. What happens is that then in that real of W axis times Z plane, this one draws actually a sphere, right? Because you have to take this circle, which lives here in the real of W axis and norm of Z axis. And take solid of revolution, right, around this axis. So what you obtain is that in the real of W axis. So in the real of W axis. And the Z plane, which, as I said, is this plane orthogonal to the real of W axis. In that space, this equality defines a sphere. Right? So this white sphere that you are seeing. Okay, and then this inequality gives you the interior of the sphere. I mean the interior of the ball bounded by the sphere, and this one gives you the complement, right? So everything outside the closed ball. All right, but now this is here, right, in the real of W axis and it times the Z plane, and we are interested in the picture where you don't have real of W axis times Z plane, but you have the circle where W runs times the Z plane, right? I mean, not times the Z plane, but actually just the disk part of the Z plane. Okay. Okay, but so how do I obtain that? Well, what I do is I see the real of W axis as the shadow of the circle, right? I mean, this circle, if I think that this circle is drawn, in the let's say X Y axis, when I take the real part, I see kind of only the shadow, this one kind of, right? I mean, I sort of see the circle, but only like this, right? And this is what I see, right? But so this is somehow the shadow of what I should see. So this means that here, this sphere is the shadow of something that looks like this somehow, like a sausage here, and also on the other side. Right? And so here, this side should be, because here it covers everything, and it covers everything because here all of this, the unit disk times 0 is in the interior of the sphere. That is, you see something like this. Right? Here somehow you can see already the torus somehow like suggested, right? I mean, somehow, let's say the equator is something like this. Right? Right? And then if you want to draw it kind of in the usual way, you don't actually draw the equator, right? this, and then something like this. Oops, and this. Okay, so here, I mean that it's very hard for me to do here, right? So here you have to imagine the torus, which is not the white part, right? I mean the torus really kind of looks something like this, as I did before, something like this, right? Okay, and then you see in the interior of this kind of two of these white sausages joined by these points. In the interior consists of the elliptic elements. The boundary consists of the parabolic elements, except here and here, right? Here. What points should be there? I leave you as an exercise to see that here these 2 points should be the identity and minus the identity. Yeah, I mean the identity matrix and minus the identity matrix, which certainly live in SU11. Okay, and all the points that are in the torus but outside these closed sausages outside are the hyperbolic elements. Now, of course, maybe you are already thinking, okay, how about loxodromic? So it turns out that if you give me any loxodromic Möbius transformation in mod plus C, that is, if you give me any matrix whose associated Möbius transformation is loxodromic, then there exists no disk which is preserved by the Möbius that Möbius transformation. In other words, if nu is loxodromic, and you have a disk D, any disk, then nu of D is not equal to D. And this means that SU11 contains no loxodromic elements, and also SL2R contains no loxodromic elements. In other words, SL2R and SU11 have only the identity. Sorry. Yeah. Sorry. If you give me a matrix in SL2R or SU11, its associated Möbius transformation is either the identity or elliptic, and then it's inside this white sausage, one of these 2 white sausages, or parabolic, in which case is kind of the skin of these sausages minus these points, or is hyperbolic, and so it's in the torus but outside these white sausages. Okay, now it is a good exercise to see then if this is SU11, then how is or SL2R, then how do the projective versions look like, right? So PSL2R and PSU11, how they look like, right? So for instance, I told you this is the minus the identity. One of them is minus the identity, the other one is the identity. So they represent the same Möbius transformation, right? So it looks like somehow you see there is some operation, maybe rotation, that identifies that with the property that whenever 2 points are identified, the corresponding Möbius transformation Möbius transformations are the same. Right? But this last part I leave as an exercise, right? Kind of knowing that this is the picture for SL2R and SU11. Try to draw the picture for PSL2R. Okay, and that's it, right? So with this we finish the section on the chapter on Möbius transformations, and we will start with models and isometries of the hyperbolic plane next class.